This session is about electricity, which is in paper 1, and the work in this covers all the work in combined and triple science. First of all, you need to know your circuit symbols and what each of these devices do. See if you can name them before the answers come up. The first one is an open switch. The next one down is a closed switch. Then there is a cell. Notice that the long side of it is the positive end of the cell. The next one down is called a battery. And the next one is a diode. This only allows current to flow in one direction. The current, conventional current, needs to go with the arrow. Then there's a fixed resistor. Next down is a variable resistor. And the last one in this column is a light emitting diode, or LED. On to the next column, the top one is a lamp, followed by a fuse. Some fairly obvious ones now. This is a voltmeter. Then there is an ammeter. The second to last one is a thermistor. And the last one is a light dependent resistor, or LDR. Electrical charge is allowed to flow around a complete or closed circuit when there's a source of potential difference to push it round. And you can work out the charge flow by multiplying the current by the time. It's written as Q equals IT. Q stands for charge, which is measured in coulombs. Current is measured in amps. And time is measured in seconds. You need to learn this equation. Potential difference pushes the charges round the circuit, and the current depends on how big the resistance is and how big the potential difference is. And we can work this out using the equation potential difference equals current times resistance. Just notice that in an exam paper they will use the term potential difference, but you can use either potential difference or voltage. So V equals IR. V stands for potential difference, which is measured in volts. Then you have current, measured in amps again. And the resistance is measured in ohms. You need to learn this equation as well. If you want to measure the resistance of a single component, you can set up the circuit. But you need an ammeter in series and a voltmeter in parallel across the device that you're measuring. And then you can work out the resistance using voltage divided by current. For resistors in series, the resistances add up, so you just add up the numbers. Try these examples. So for the top one, you have 4 ohms and 6 ohms. This gives you 10 ohms. The second one is 14 ohms and 16 ohms. This gives you 30 ohms. The third one down is 240 ohms and 170 ohms. This gives you 410 ohms. Notice in the last one that it's 17 kilo ohms and 68 kilo ohms. So this one gives you 85 kilo ohms. For resistors in parallel, the total resistance is smaller than any individual branch. So for example, the top one is 12 ohms and 12 ohms. So the total resistance has to be less than either of those. So is 12 ohms. In the second one, it's 12 ohms and 6 ohms. So in this case, it has to be smaller than the smallest branch. So it's smaller than 6 ohms. The third one has equal resistors again, so again it's less than 47 ohms. And notice in the last one is 1 kilo ohm and 300 ohms. 300 ohms is smaller, so it has to be less than 300 ohms. As a wire gets longer, the resistance increases. And we did an experiment with this, where we looked at different lengths of wire and measured the current and voltage across them. So we connected 10 centimetres of wire. We set the current to about 1 amp so the wire doesn't get hot. And we made sure we switched off the current between readings, again so the wire doesn't get hot. And then recorded the voltage for 1 amp. And repeated this for 20, 30, 40, 50, 60, 70, 80, 90 and 100 centimetres. And calculated the resistance for each length. The other experiment we did was to look at how the resistance of a component changes. We set up the circuit here, and you need to know this circuit. It has a fixed voltage, but then we can vary it using the variable resistor. The ammeter is in series, and the voltmeter is across the device to be tested. We changed the variable resistor to change the potential difference, recorded the current, and plotted a graph of current on the y-axis against potential difference on the x-axis. The first one we looked at was a fixed resistor, and you need to learn this graph. This is called an ohmic conductor. At a constant temperature, the current is directly proportional to the potential difference across the resistor. This means if you double the potential difference, you double the current, and you'd see it as a straight line graph through the origin. This means that the resistance of the resistor does not change. The second one is a filament lamp, and again you need to learn this graph. The resistance of a filament lamp increases as the temperature of the filament increases. As the potential difference increases, the lamp gets hotter, the fixed ions vibrate more, so the electrons collide more, increasing the resistance. The last graph to learn is a diode. A diode only lets current flow in one direction. In the opposite direction, the resistance is very high. A thermistor is a resistor whose resistance changes with temperature. With a high temperature, it has low resistance, and with a low temperature, it has high resistance. Notice the symbol for a thermistor and the graph of how the resistance changes with temperature. Another device you need to know is a light-dependent resistor. Here, the resistance changes with the amount of light. So when it's bright, it has low resistance, and when it's dark, it has high resistance. Again, notice the graph and the symbol for this device. So there are some rules for series circuits. In a series circuit, the current is the same through each component, the potential difference is shared between the components, and the resistors in series add up. Let's look at an example to see how this works in practice. So for the circuit in the top right-hand corner, each cell has a potential difference of 1.5 volts. You need to calculate the total resistance of the two resistors, the total potential difference of the two cells, the current through the battery, the current through resistor P, the voltage across resistor P, the voltage across resistor Q, and what you notice about the voltages across resistors P and Q. So first of all, for the total resistance, question 1. All you do with resistors in series is add them up. So in this case, the total resistance is going to be 12 ohms. The same happens for the cells for question 2. The two cells are in series with each other, so they just add up too. So you've got 1.5 plus 1.5, which gives us 3 volts. So now we can work out the current through the battery. We have the total resistance of the circuit and the total voltage, and we do voltage divided by resistance. The voltage was 3 volts, the resistance was 12 ohms, so our total current is 3 divided by 12, which gives us 0.25 amps. To work out the current through resistor P, we have to remember our rules for series circuits, because the current is the same the whole way round. So this is 0.25 amps. This allows us then to work out the voltage across resistor P, as we know the current through it and the resistance across it. So we can work out the voltage using current times resistance. 0.25 amps times 2 ohms gives us 5 volts. We can do something similar for resistor Q. The current through it again is 0.25 amps. So as we know the current and the resistance, we can multiply them together. 0.25 amps times 10 ohms, and this will give us 2.5 volts. What do you notice? Two things about these voltages across resistors P and Q. First of all, if you add them up, they come to the total voltage of the supply. So 0.5 plus 2.5 volts gives us 3 volts. The other thing you notice is that the voltages are actually shared in the same ratio as the resistors. So the bigger the resistor, the bigger the share of the voltage. There are some rules for parallel circuits too. In a parallel circuit, the potential difference is the same across each branch. The current entering a junction is equal to the current leaving a junction, and the total resistance is less than the resistance of the smallest individual resistor. So here's a worked example. In this case, you have to look at what the voltage is across R and the current across R1, then across R2, then across R3, and then we're going to look at the current through the battery and the total resistance of the circuit. So first of all, voltages in parallel. If you remember, voltages in parallel are the same across each branch. So as there's 6 volts across the supply, there'll be 6 volts across R1, 6 volts across R2, and 6 volts across R3. So the answer to the first question is just 6 volts. To work out the current through R1, we have the voltage and the resistance, so all we do is divide the voltage by the resistance. So we divide 6 volts by 1 ohm, which gives us 6 amps. We can do something similar for R2. R2, the voltage across it again is 6 volts, and the current can be calculated using voltage divided by resistance. 6 volts divided by 2 ohms this time, giving us 3 amps. R3 again has 6 volts, and we can work out the current in the same way. This time it's 6 volts divided by 6 ohms, and we get 1 amp. So what's the current through the battery? Well, if you look at the circuit, all 3 currents join together by the time they go through the battery. So we need to add them all together to get the total current through the battery, which gives us 10 amps. Once we know this, we can use that voltage and the total current to find the total resistance. Resistance equals voltage divided by current, which is 6 volts divided by 10 amps, which gives us 0.6 ohms. Just notice that this is less than any of the individual resistances.